Okay. Assignments, and basically after each lecture, when I teach you the materials, and hopefully I can teach you well, and you understand the materials, and you ask me questions if you don't understand something, based on each lecture, I'm going to ask you some questions, and you can easily answer those and get extra credits. How does that sound? Okay. And most of the class are doing well. And again, as I said, and that statistics that I had was excluding the makeup quiz and also makeup exam and extra credits for going to tutoring. So I'm thinking that most of you are doing well in the class. But again, I want all of you to get A's, or like worst case scenario B, or for those of you who are really struggling, C's. So hopefully we end the semester on good note. And I posted yesterday your next homework 13, which is due this Wednesday. And after that, we'll be having one more homework, one more quiz, one exam, and your final exam, and then the semester will be over. Just like reminding of these facts. So before I start the lecture, any questions from previous lectures? No questions? Okay. And I also included another slide in this, but apparently I didn't email it to myself, so it doesn't worth to just go through all the pain and then take the class time for that. So we have roughly 6 students that are failing, but 3 out of 6 are really close to passing. And my aim is that not to fail anyone. And if you listen to me and follow my instructions, hopefully that's not far from reality, because I'm going to assign extra credit. Okay, so if no question, can anyone tell me what was Bronsted-Lowry acid? Exactly. So remember, like, as you learned in your previous courses, chemistry courses, I guess, HCl, right? HBr. I'm telling my 101 students anything that has H is an acid, which is not entirely correct, but is not entirely incorrect. So you see, as I said, we call H plus proton. Okay? So when something has H and it can donate it, we call that Bronsted-Lowry acid. And the opposite is when, one substance can accept proton, we call that Bronsted-Lowry base. Okay? So in the questions that I'm going to ask you today, I gave you this equation, the exact same thing. And I told you which ones are acids, which ones are bases. So what you do, and I wrote that as H2O plus HCl, kind of equilibrium sign. And then you have like these arrows, not the same length, because HCl is a strong acid. So this reaction proceeds more left to right compared to right to left. Does that make sense? So this is what it means when the arrow, one of them is like longer. And that gives H3O plus Cl minus. And I told you which one of these species, which one of these, substances that you see here are acid. And I had like so many students in my 101 class confused, what is a species? It's an element. So any kind or sort of thing, we call those a species. So water, HCl, H3O plus, Cl minus, all are species, okay? So if I ask you which one of the following are acids, which ones are acid? HCl and hydronium. H3O plus, right? And we call, if you have an acid and then it loses the proton, we call the equivalent on the other side of the equation conjugate base. So remember, if HCl is an acid, Cl minus should be a base, okay? Or here, H2O, if it's a base, in this example, H3O plus, the equivalent, when it gets a proton, that would be, the conjugate acid and general acid. Any question about that? Good? Here, we didn't have the arrows in the same length, right? This one is more favorable. So Cl minus doesn't have the same amount of tendency to produce HCl. Okay. And here again, it's kind of like review of what we talked about before. And can anyone tell me how can I compare different acids? So I want to see which one is stronger. Yes?
Isn't it how easily they dissociate in water?
Exactly. So when they dissociate more, when you see more of H3O plus, what does that mean? What constant did we refer to compare those things?
Ionization.
Exactly. We had ionization constant or acidity constant. And when this value is larger, if Ka is larger, it means we have a stronger acid. Because as your friend mentioned, it means that this acid is being dissociated more or dissociates more in water. Any questions? Good. And we said most of the time scientists or chemists in this case, they don't want to deal with negative powers. So instead of saying 10, you see that power of minus 14 or 10 to the power of minus 17, they came up with a definition that is pKa. And that is just memorization of what pKa means. So P of anything, okay, the screen was moving when I was doing that. P of anything is minus logarithm of that thing, okay? And I posted a video for you to watch in case you forgot what logarithm was. But if you have, for instance, 10 to the power of minus 17, okay, if you call that A or B or whatever, okay, logarithm of something means that you can write this expression as logarithm of A, and then so the final answer of what you are having, you put that in front of logarithm, and here the base that you had here comes here to the base of logarithm, and then minus 17 is what the function logarithm is. So logarithm is essentially the power, the exponent. Does that make sense? Do you remember what it was from previous courses? Anyway, so in this case, in this course, everything that we're dealing with is like 10 to the power of something. So the base of logarithm is 10, okay? So if I have 10 to the power of minus 5, okay, and I take the logarithm of that, logarithm of 10 to the power. So what is that? Does that make sense what I'm saying? So here we had 10 to the power of minus 17, right? So here instead of A, right, instead of A, I can write, 10 to the power of minus 17. So this is basically, let me change the color. I can write logarithm of A. My A is 10 to the power of minus 17. Can everyone see that? And then my base is 10. That became minus 17, right? So basically, this tells me, when I take the logarithm, it tells me what is your power, what is your exponent, right? Or you can learn it like this, that when we don't write the base in logarithm, it means that the base is 10, okay? And this expression is basically 1. Because 10 to the power of 1 equals 10. So remember, the function logarithm is power. So in this number that I have here, what is the power? -5, right? Does that make sense? And here, when we have p of something that is minus logarithm. So if I give you my 10 to the power of minus 17, you remember she said logarithm is power, is the exponent. What is the exponent here? Minus 17, right? But p function is minus logarithm. So what would be the answer here? 17. Does that make sense? Good? Any questions about this? Okay, if no question, if I ask you which one of these numbers are bigger? 10 to the power of minus 17 or 10 to the power of minus 15? 10 to the power of minus 17 is bigger, right? Because when you're dealing with power, when the power numerically is bigger, we have like a bigger number, right? And minus 15 is bigger than minus 17. Or you can refresh your memory in mathematics that any number to the power of negative is the reverse to the power of positive, right? It's basically comparing these two numbers. And when you have two ratios that the numerators are the same, the one that has a smaller denominator is bigger, right? So this one is bigger. However you want to compare, but you should get the same answer. So if I tell you, give you two numbers, this and that, and I say two acids have these acidity constants, which one is the stronger acid? And I call this A, call this B. Which one is the stronger acid, A or B? B, right? Remember, we said the acidity constant, when it's bigger, it means that our acid dissociates more in water, right? So the concentration of hydronium ion or H3O plus or proton is bigger, so the acid is stronger. Okay, so this is kind of opposite of what I said here, basically this. So I said bigger, Ka, or write it, bigger acidity constant means stronger acid. So your book wrote the same thing, just the opposite. Smaller Ka means weaker acid, right? Is that clear why? Any questions? Now, so we established this acid is stronger, right? If these numbers correspond to acidity constant. Now, what is pKa of these values? Can anyone tell me? What is pKa of 10 to the power of minus 17? What is pKa of this? So we established this one is a stronger acid, right? That fact don't change. And now which one is a stronger acid? Lower pKa or higher pKa? So here, this one is a stronger, right? And then the pKa is lower. Okay, so lower, or I guess smaller pKa means stronger acid. Because pKa and Ka, because of that negative in logarithm function, they have opposite trends. Any questions? Does that make sense? And this is exactly what your book said, that larger pKa means weaker acid. And as we said, there is an inverse relationship between the strength of an acid and the strength of the conjugate base. So when you have an acid like HCl, hydrochloric acid, right, that is really strong acid, what is its conjugate base? Cl minus, right? You remove the hydrogen, that would be conjugate base. So if you have a strong acid, the conjugate base would be weak. Okay? Because by the same rationale that HCl is willing to lose its proton and produce a Cl minus, Cl minus doesn't have that much tendency to, get hydrogen and produce HCl. Kind of like the equation that I wrote in the previous slide. Any questions? Good. So as I said, all of things that I'm talking about now, I'm going to ask you at the end of the class, and you can easily get extra points by answering them. So kind of 3 points. So let's test if we learned what I talked about. The Ka for ethanol is 1 multiplied by 10 to the power of minus 16. What is its pKa? 16, right? You say minus logarithm of this number, which would be, as I said, so 1 multiplied by any number is 1, and then this part is 1, so it would be plus 16. Okay, so the pKa's of hydrogen cyanide and acetic acid are 9.2 and 4.7 respectively. Which one is the stronger acid? Which one? Exactly. So this one, pKa lower means the stronger acid, right? I'm going to write pKa, or like smaller, means stronger acid. So you compare these two numbers and then see which one corresponds to which one. So this one was 9.2, this one is 4.7. So acetic acid is stronger. And make sure in exam, pay attention which one is which, because sometimes you know the answer, but you just see 4.7 and say, I don't know, the first one. Just like make sure to pay attention. Any questions? And here, I just wrote the answer, I guess in a nicer manner, you can say. Okay. We briefly talked about Lewis and acid bases. Can anyone remember what was an acid based on Lewis definition? So we said based on Bronsted-Lowry, if we had like HCl, and you can always in exam and for all your courses, if you remember one example, you can expand it to other examples as well. If you remember, HCl is an acid and it has proton, right, H+. So that is an acid, you know that, right? And based on, these definitions, usually they are consistent, right? So they're not contradictory much to each other. They can have exceptions, but in general, if HCl is an acid, it's an acid with all the definitions. So here, it can donate the proton. So proton has a positive charge, right? If you consider HCl as H plus Cl minus. If some substance can donate H plus, the equivalent in the charge language, I guess, if something wants to lose positive charge, it means that it likes to gain negative charge. Does that make sense what I'm saying? Any questions? So based on Bronsted-Lowry definition, acid wants to donate proton. Based on Lewis definition, Lewis acid is an electron pair acceptor. Okay, it wants to accept electron pair. And base would be the opposite of that. So if acid wants to accept electron pair, base would want to donate electron pair. Does that make sense? So here, based on, and in most of these examples, because we have some substances, they can be acid or base, depending on what reaction we have, some substances can be base in one situation or acid in another. That's why sometimes, I accept acids and bases that are well established, like hydrochloric acid, HCl. We know it's acid regardless. But for water, for instance, I give you the equation so you know in this situation, is it an acid or base? So in this equation here, you see H plus water gives H3O plus, right? And I can write this equation as this. So H plus, do you think H plus accepts electrons or donates electron? So let me ask you this, hydrogen atom, how many electrons it has, hydrogen atom in periodic table? 1. What about proton or hydrogen ion? How many electrons it has? It doesn't have any electron, right? It lost its one and only electron. So can it donate any electron? It doesn't have any electron to donate, right? It's kind of like someone that doesn't have any money. They cannot donate if they don't have any money. So proton cannot donate. For that matter, it's not a base. It's an acid because it accepts electrons. Okay, and most of the time, in most of the examples that I give you, anything that has a positive charge wants to accept electrons. So it would be an acid. Does that make sense? And most of the time, when you have a substance or compound that it has non-bonding electrons, for instance, water in this example, it can donate, these electrons, right? So would it be an acid or a base? Remember, electron pair donor is a base, right? So for that matter, water in this example would be a base. Does that make sense? Any questions? Okay. So I have some bullet points here, and as I said at the end of the lecture today, I also included screenshots of your book, which is basically, I did that last session too. And so make sure you have the materials and then study them. But I also have some bullet points here to make sure that you know the materials and I can talk about them in the class. So basically what I just told you before, your book kind of wrote that here. Any atom with an unshared electron pair can act as a Lewis base because they can lose those electrons or share them with the other atoms, right? We said anything that is electron pair donor is a base. Just anytime, if you have any questions about anything, just feel free to ask me. Compounds with an element whose valence shell is incomplete act as a Lewis acid because they can accept electrons, right? If their valence shell is incomplete, they can accept electrons, so as a result, they are Lewis acid. Okay? And here is something that I also asked you in your, at the end of the class, extra credit assignment. I don't want to call it quiz to scare you, but I have that in the questions that I'm asking you. So water acts as a base towards acids that are stronger than itself. So as I told you, some compounds like water, they can be an acid or a base. So I had equation that I wrote for you before that water was a base. There was another equation that water was an acid. So water, when it's in proximity with substances or compounds that are stronger acid than itself, like hydrochloric acid, it acts like a base, okay? And it acts as an acid toward bases that are stronger than itself, like ammonia. And we call water an amphoteric compound, okay? So in general, substances that can act as either an acid or a base are called to be amphoteric. So if you have those substances that are amphoteric, if they are reacting or if they are, in proximity with acids that are stronger than themselves, they would be a base. If they are in proximity with compounds that they are stronger bases than themselves, it would be acid. So they have kind of dual properties. They can be an acid or a base depending on what they are dealing with. Any questions? And as I said, I asked you exactly the same sentence at the end of the class. Any question about that? Good? Okay, when I don't hear anything, I assume we're good. Now, let's work on this example. Which of these followings are acid based on Lewis definition? Which one are bases? So first, can anyone tell me what was acid based on Lewis definition? Exactly. What is a base? Exactly. Donor. Okay, so Mg2 plus, do you think it accepts electrons or donates electrons? Accepts, right? It has like positive charge, so it's an acid. And we're talking, in the Lewis context, so it's a Lewis acid. What about CH33C? I think that is a, okay, I think I have this here, so we can just neglect that. What about CH3NH2? So how, if you see something that it doesn't have a charge, right? So what is the best way to know if it's an Lewis acid or Lewis base? So, do you remember any other concept that it has Lewis in it? Uh-huh. Yes.
Like an open valence shell.
Uh-huh. So how would you see those things?
Oh, like the Lewis dot structure.
Exactly. If you have the Lewis structure, it helps us to see what is happening, right? So if I have CH3, NH2, right? So what is the valence of? So how many electrons nitrogen has here as the structure that I wrote? So it has like 2 here too, right? Non-bonding. So if you draw this structure, based on this, do you have an acid or a base? Exactly, you have a non-bonding electron here that this compound can donate, right? So it is an electron pair donor, right? Remember that if you have non-bonding electrons, your compound would be a base. So this would be a Lewis base. And I think I add here Lewis acid because that's the definition that we're following. What about Zn2 plus? Acid, right? When you see a positive charge, then you can accept electrons, right? What about this compound? So CH3, and I always advise all of you and myself to draw the structure to see what is exactly happening. So what is how many electrons oxygen has here? Right? So it has like 2 non-bonding pairs, or like 4 non-bonding electrons in total. So what is this one? Base, right? Lewis base. What about this one? Do you remember what this one was called? I guess I go the other side so it won't be confusing. So a carbon that has a positive charge and is attached to 3 different metals. Do you remember what we call these? Can anyone remember carbocations? Right. So what do you think about this one? Can it donate electrons or accept? Accept, right? Because it has a positive charge and it can accept. So what would that be if it's acceptor? Exactly, Lewis acid. And then here, this one is a little tricky, so I need you guys' attention. So CH3, 3B, boron. So basically we have boron here and it has 3 methyl groups. Okay. And it doesn't have non-bonding electrons. So this one is an exception from Lewis structure. This is the structure of it. And it doesn't have non-bonding electrons. Okay? And it can accept 2 more electrons from another compound. So for that matter, because it's an electron pair acceptor, this is also Lewis acid. Okay? So I just asked you to remember this one, and this is its Lewis structure. And finally, CH33N. So CH3. I guess I can just like do this similar structure that I did for the previous one. CH3N. But in this case, we have the non-bonding pair here. Okay? So CH33N has this non-bonding electron to donate. So would it be an acid or a base? Okay. So as I said, the only tricky one in my idea is, be CH33 or CH33B boron, because of the exception from octet rule. Any questions? Good. And as always, in the next slide, let me see here. So for that matter, this structure, as I said, this one is the tricky one, which is an exception from octet rule. And the boron has only 6 valent electrons around it, and it can accept 2 more. Okay, so this example I just want you to remember. Okay? Because these are like the more organized, with more explanation of each of these. And this one is the one I think that is like the trickiest. But other than that, if you write the Lewis structure, most of them, at least these ones that I wrote here as an example, they are consistent with octet rule. So you can have the Lewis structure and then based on non-bonding electrons, decide if they are an acid or a base. Okay? Good? Okay. Now I'm going to progress more with the lecture and talk about acidity of alcohols and phenols, right? We talked about how to name alcohols and phenols, and then we learned about acidity and basicity. For some of you, it was mostly review. For some of you, you didn't know them, and we talked about them. So now we learned the tools to talk about alcohols and phenols and compare their acidity, okay? And like water, as we said, water is amphoteric, and as we progress with the nature, you see that alcohols, are amphoteric too. But for now, based on what our book says, alcohols and phenols are weak acids. Okay? So if I give you, a strong acid and an alcohol, for instance, if I give you ethanol and hydrochloric acid, and I tell you which one has the higher acidity constant, which one would have higher acidity constant? Hydrochloric acid or ethanol? I'm asking which one has higher Ka. Exactly. HCl, right? So are we good with like Ka, pKa, which one is a stronger? Okay. And hydroxyl group can act as a proton donor, and dissociation occurs in a manner similar to water. As I said, we can consider alcohols to be acids, but they are weak acids. So if you consider the structure of alcohol in general, they have like an OH group, and we can consider this proton to be dissociating in water. So you have like RO minus and H plus. Okay, kind of like similar to what we talked about before, right? Not so much new information, just like rewriting that for alcohol. And the conjugate base of an alcohol is called an alkoxide ion. And this is another thing that I asked you in your quiz that I'm going to give you momentarily, like in 5 minutes or so. So remember, you have alcohol, right? That is you can consider that to be an acid, and then you call this one RO minus, that is a conjugate base, right? And we call that alkoxide. Just terminology. Any question? Good? So far, so good. Okay. And here again, I wrote the information that you need to know, and also I have like your book at the end of these slides. And phenol is much stronger acid than ethanol. And the reason is that, do you remember that I told you if you have an acid that is a strong acid, the corresponding conjugate base would be weak base, right? So if you have like a weak acid, the corresponding conjugate base would be strong. Do you remember? Just like previous slide. So now I'm telling you, phenol is much stronger compared to ethanol and alcohols in general because their corresponding conjugate base is really stable and is stronger. So what I mean is that if we have like the conjugate base of phenol, which is basically if we remove the hydrogen, right? Do you remember the resonance structure that we talked about when we had a benzene ring? So when you have like a negative charge here on a conjugate base of a phenol, this charge can be delocalized in the corresponding ion, and we call that phenoxide. Okay, so we have phenol, which is an acid, the corresponding conjugate base, we call that phenoxide ion. Okay, and because of the delocalization of this negative charge and this resonance structure that phenoxide ion has, this structure is much more stable compared to alkoxide ion that I just showed you previously. Okay? Because the structure of this phenoxide ion is really stable, okay? The phenol is much stronger acid compared to ethanol. It's as if these ions want to be generated more. So phenol would be dissociated more in water. Does that make sense? And if it dissociates more, we have like more hydronium or like proton in water compared to ethanol. Any question? Good? Does that make sense? Okay, so basically what I just said, phenol is much a stronger acid than ethanol, mainly because the corresponding phenoxide ions are stabilized by resonance. And the negative charge of an alkoxide ion is concentrated on the oxygen atom. Remember, alkoxide was the conjugate base of alcohol, right? But the negative charge of a phenoxide ion can be delocalized to the ortho and para ring positions through resonance. Okay? So this structure, because it has resonance, most of the time when you have a resonance structure, is much more stable than other structures if you didn't have this resonance structure. For instance, if you have like cycloalkane. So this structure is more stable. Any questions? Okay. So I also included this link here and then kind of like explaining more about why is phenol acidic and properties of phenol as an acid, and kind of like explaining in more detail about the previous slide that I showed you and why this negative charge is delocalized and ortho and para positions on phenoxide. So if you want to have more information, I highly encourage you to look at this link here. Okay, and as I said, I have like your book here. Hopefully I don't go to jail for doing this. So the publisher will be so angry at me. Students didn't buy my book, she just gave them for free. Anyway, so at least read them. So. Because, you know, and I had your friends telling me that reading the book is much more effective compared to just listening to the lectures, I guess. Can you pass one? You can start answering the questions, but it shouldn't take long.
Oh, yeah.
Everyone has one? Okay.
Of course.
So hopefully you can answer all, but if you think that you cannot answer all of them, just let me know, and I guess I consider the first 5. I guess we'll see. Okay, and for people who are watching this at home, I gave students 10 questions for extra credit. So if you're watching the lecture, just email me so I give you those as well. I just you can keep the quiz, but give me only the chance, but write your name. Thank you. Thank you. Thanks. You can have the questions, just give me the questions. Yeah, thank you.
Thank you.
Thanks. Thank you.
Thank you.
Thank you. Thank you. Thanks. You can just give me the Scantron. The other one you keep to study. Thank you. Thanks. Thank you. Thank you. Just give me the Scantron. The
Oh,
other
sorry.
one. Yeah, the other one. Thank you. Thank you. Thanks.
Thank you.
Thank you.